Okay, let's start now. So last class we started talking about generalization and we wrapped up the section on backpropagation and automatic differentiation. And the backprop is probably one of the most important topics in neural networks. It's the backbone of neural networks. It's the machinery that makes neural networks scale and work well. Uh, So first of all, any questions on the backprop section? Is are the calculations, do they make sense, or any questions about the backprop rules or the algorithm?
I guess I do actually have one question.
Yeah, go ahead.
It's just a different kind of way of writing the backpropagation algorithm that I had seen before that I just
Yeah,
wanted to share with you in the chat to see if it's correct, essentially. So
sure.
I'll take a
Uh,
screenshot of it and send it in the chat.
yeah, and if I cannot respond by class, I'll respond to you after looking at it.
Okay,
And
no
so
problem.
the thing is that even myself, like when I was in college, when I first learned backpropagation, we called the course pattern recognition. It wasn't even called deep learning or neural networks. And we also learned backprop in a different way. The way I've taught you as backpropagation as reverse mode automatic differentiation. This is a very modern view of backpropagation. Uh, so it may not be the same that you would see in a classical textbook. But the way I've taught it is how backprop is implemented in all the modern deep learning libraries like PyTorch and TensorFlow. Kind of this view of a computation as a graph, and then basically running chain rule from the end to the front. That's the more general view. And in textbooks, what you would see as backprop is just backprop for a multi-line neural network. And that gives you specific equations for the backprop or the gradients. So that I believe is what you would see in textbooks. And in class, I tried to kind of show you some of that. Right. For sigmoid, uh, there is a specific derivation. And actually, I want to share with you this link. So uh, neural. So this is actually an excellent resource of backpropagation. And this section, if you look here, then this will also have a derivation of the sigmoid neural network. So, Bobby, you can also check this one. I'll share it in the chat. So please take a look at this one. And you can also match your equations. Uh,
Okay, yeah, that
s-
sounds good.
yeah. And otherwise, I'll also take a look at your notes and give some comments. All right, but this book is an excellent resource. I think I've linked to this at the start of the course, but you should, if you have time, you should also try to read through these chapters. These are one of the best explanations of deep learning and neural networks that I've seen. So do try to take a look at this. Uh, all right. One thing I wanted to kind of talk about is as I was doing this calculation last class for a multi-layer neural network, I think there are some there is there I tried to solve one bug. I think there is still another bug. Can anyone did anyone figure out or kind of try to redo these calculations and find encounter any bugs here? It's specifically related to this calculation where we do the hidden vector times the weight dot, and then we get the activation, and then we pass through a ReLU, and then we get the final output y. And we are trying to do the gradient calculations through this network. Eventually, I don't think I need this Hadamard element-wise multiplication. It should be something simpler. Although the Hadamard does appear in some derivations, but in this case, I think we don't need it because I made a mistake somewhere, especially here. Any ideas? if you need a hint, I believe there is a dimension inconsistency here. So if no one wants to try it, I'll try to explain what I might have done wrong here. So what I'm trying to do here is, what are we doing here? We are basically going through a multi-layer neural network, right? And then we have our input x and weight that goes to the first function, which is a ReLU block, which does w1 x and then max of that with 0. And then we expect to get like the first activation h1, which I'm saying is a vector. But operation I'm doing here is a weight. I'm saying w1 is also a vector and x is a vector, so I'm doing a dot product, so I'm getting a scalar, not a vector. So my mistake is I say w1 is a vector, but actually it should be a matrix. And then if it's a matrix, then w1 times x would give you a vector h. So that was the bug that I had here. So I'll just try to uh, maybe I'll just try to just redo that part to make sure that uh, so what we have here is so we have our input, which let's say is in RD. And here we have a multiplication, but it's a matrix multiplication. The second input is the parameter, but it should be a vector, let's say w1 here. And that should be in RD times D, right? And then from here, I get a reactivation A, which is a vector, and this is going to be, let's call it A1, and this is W1 vector times matrix. And then this we can pass through a ReLU. And outward we would get, let's say, H1 bar. Okay, so this is like one block, and we can compose multiple of these blocks to get different layers. So this is like the first layer of a neural network, and then we'll have a few more layers like this until we reach the final output. So let's look at the uh, backprop here. So let's say we are trying to do backprop here. So how would we start the backprop for these two blocks? Our goal is to compute these quantities, right? We want to compute, let's say, dw1 and dx1, right? Because those are the downward gradients that we need. So the gradient starts from here. So what gradient will be passed down here into this ReLU? Yeah, Bobby.
Would that be the like the weights and the activation from the pre or from the layer ahead?
Yeah, the layer ahead, but basically the way to remember this is that if you're passing H1 into the upward blocks, down, then what you get back is D of H1, right? That's what you're gonna get passed down here, and then you pass it back here. So what is D of H1 is just basically your finally you have the loss, and this is just loss with respect to D of H1 bar. Okay. And we said this will be a row vector. So that's what comes here. And then we pass through the ReLU. And when we pass through the ReLU, we have to multiply when we get back here, what we need is here we need to compute d of a1 bar, right? So how do we get d of a1 bar? That is actually by definition del L by d of a1 bar. And now we can apply the chain rule. So this will be d of L divided by d of h1 times d of h1 divided by d of a1, right? Now this part is what? This part is the upstream gradient that is passing through here. So this is d of h1 bar. And what about this quantity? What is this? Can anyone tell me what this would be? So h1 is the output of ReLU and a1 is the input to ReLU. So this is the Jacobian or the derivative of the ReLU network, of the ReLU function. So from last class, does anyone remember what the derivative of ReLU is?
It's just the input, right? Is that correct?
It's the indicator, right? So if you remember what ReLU was, so you can just look back here, I think. So here we actually did this, right? So ReLU of x is x if x greater than or equal to 0 and 0 if x less than 0. So if you differentiate, then if x is positive, then the derivative is 1, otherwise it's 0. So that means it's just the indicator function, that indicator of x greater or equal to 0. Okay, so if we apply that, then this will be just the indicator function of input the activation 1 to be greater or equal to 0. Okay, and now how do we actually say whether a1 is greater or equal to 0? The ReLU is a pointwise operation, right? So here, if x is a vector, then x greater or equal to 0 means that you basically run ReLU through all your inputs in a vector, and for each one you individually compute whether x is greater or equal to 0 or it's not, right? So kind of the way to think about this is like, let's say you have a vector, let's say a1, right? So a vector, let's say it has two components, a1, a2, right? And then the if you want to differentiate with respect to ReLU of this a vector, this will actually be uh, it's going to be identity of I think I need to do a bit better job with my notation. Okay, let's just do this. Let's call this is A1. So A11 is the first component and A12 is the second component. And then this ReLU is going to be whether A11 greater or equal to 0. So that's for the first entry. And then the second entry is for A12 greater or equal to 0. Okay. And as a shorthand, you can write it in this form as a vector greater or equal to 0. But it means that every component it has to be greater, whether testing whether every component is greater or equal to 0. So with this, we get dA1. And now we need to compute dW1, right? So how do we write dW1? dW1 is dL by dW1, right? And that's going to be equal to dL by dA1 bar, then dA1 bar divided by del W1, right? And A is W1x, so dA1 by dW1 should be what? From this equation, what is the derivative of A with respect to W1?
X.
It should be just X, right? So del L by del W1 we got from here. So this is, we just plug in the value D of H1 bar, and this is X bar, the input, and we have the identity here that mu1 bar greater equal to 0. So what we have to do here is now check the dimensions, right? So dW1 is the derivative of a matrix W1. So this has to be D by D. DH1 is what is DH1? DH1 is a gradient and it's a row vector. So it's going to be 1 by D. And X is a column vector. So it's D by 1, right? So to make this work, what we need is basically we just need to reverse this, right? So this X should actually come here in front, and this should go here. That way we have the proper dimensions. So if this should actually be X bar times D H1 bar. Then you have a D by D matrix and followed by an indicator. Okay. And you can also similarly find the gradient of X bar in a similar fashion. Okay. So hopefully that is clear. All right. So do go through these calculations and see whether they make sense. Also, I encourage you to kind of go through that video of Ambesh Karpathy on backpropagation. That's the best resource. And also, this book has a nice chapter on backpropagation, which you should read for if you have any more confusions. All right. So I just wanted to do that clarification, but now let's move on to the today's lecture topic, which is generalization. Okay. So we started talking about generalization last class, and what it basically means is we train a network and we want to test it on new unseen data. And if we get good predictions on new unseen data, then we say that we have a good generalization capability, right? And so that's the goal here. Uh, so there are kind of two metrics that we are concerned here, which is one is the train error and test error. Okay. Can anyone tell me the definition of training error?
So the number of iterations that you go through, right? You would plot your loss
Mm-hmm.
compared to the number of iterations. And
Yeah.
and you should, if your algorithm is correct, you should see that go down.
Right. You're talking about the training loss, right? So the trainer basically is the number of mistakes you make on your training data, right? And the plot that you're mentioning is kind of like this plot, which is for the training error, right? And this is also called the train loss. But the definition of this is that, let's say you are doing classification. So initially, before you've learned anything, right, you just use random weights and you haven't adjusted any of the weights. So that's where you expect to have high loss because you haven't really trained your network. And then as you do gradient descent, after doing backpropagation of your network, you gradually kind of lower your training loss. So basically, what you're doing is that you are uh, trying to adjust your weight such that you are fitting or correctly classifying all of your training data points, right? So if you let's say your network is called F, it's your network, and you have an input vector Y, right? So let's say that is your final prediction of the network, and then you expect this to match your label Y, right? So if this matches your label Y, then you have the number of the lower the number of mistakes you make where your prediction f of x1 is not equal to y1, the better training error, the lower the training error and the better is your training performance, right? But what is test error? Test error means that it's a new input, a new input that you haven't used in your training. Let's say it's x and y, right? And you want to check whether does fx, the prediction on this new input, is that equal to your predicted output or not. So if you have a bunch of these test examples and you don't do well, that means that you haven't really generalized your network, because you might be able to get the training error to go down by using backpropagation and gradient descent, but unless you have a good generalization in your system, you may not get good test error. So you might have high test error and low training error, and that would mean you're actually overfitting and you're not actually generalizing well, right? So low error plus high test error, that means you are overfitting, and that's bad. Overfitting means you are fitting to noise specific your training examples, and you're not actually learning the general pattern of your data. So to combat overfitting, we need to use techniques to improve the performance of the neural network, and that's what we're going to discuss. Uh, so what does the picture look like? Uh, so you have this test training error, and then if you plot the test curve, then this is usually what happens. And then I'm going to explain this, but on x-axis, I'm going to say I'm going to plot capacity, and here it's going to be the loss. So the loss that is going down is typically the train loss, and the loss that is goes down then goes up is the test loss, right? So you have this kind of threshold region, and this gap here, as you kind of, so what is happening here is on the x-axis I'm plotting capacity or size of the neural network. So in general, we understand that if you have more parameters in your network, then you are able to fit more complex functions, and you will be able to actually lower your training loss to almost zero, right? Uh, and kind of one example that we saw here is that if you have, let's say you have a true function which is like a quadratic, and you have a bunch of these, like let's say samples plus noise, right? And if you use a very complex function, you might end up with something like this as your learned function, right? So what it's doing is that it's actually passing through all your training data, but you can see that uh, this quadratic was your true function, but we had some noise, but the because you're allowing really complex functions or high dimensional polynomials to fit this data, you're actually fitting to the noise and you get a really complex shape here. And that's a classical sign of overfitting. You're overfitting to the noise on your training data and you're not learning the general pattern. Here, the general pattern is a quadratic. So this is where you would be overfitting. Okay, right. Any questions so far? All right. So now we understand the problem, right? So uh, what do we do about it, right? We need some mechanisms to fix the problem. Okay. So one thing that we talked about last time is that we can do something called early stopping. Okay. And the observation is that uh, as we are like training a network, right, we might kind of get the loss to real zero, but if we don't drive the loss towards really low values, we have a chance that we will not pass this threshold regime where the test error starts to grow, right? So if you stop, let's say somewhere here, then likely the gap between the test and error is still within our bounds, and we might be able to generalize well. Whereas here, the gap is much higher, and that's not where we want to be. So we were stopping early, we can try to prevent overfitting and have better generalization. Right, so that's a common technique. Uh, how do we actually do this in practice? In practice, you would kind of maybe run multiple multiple experiments where you try stopping at different points and see what your performance is. So you kind of uh, in your data set, you might have a held out test set, and you train using your training set and then test using your test set, and then you measure the test performance and the train performance and the gap between them, right? And if that gap is high, you mean that means you're overfitting. So then you maybe next iteration you try to stop earlier, and then you kind of measure the performance. So by trial and error, you can or experimentation, you can find a good stopping point. Okay. Or like as you're running the experiment, like and any iteration, you keep track of every iteration, and you also kind of checkpoint your weights. And then when you see that the test error is starting to increase, that's where you stop, and then you go back to the last point where your test error was the lowest value, like this, something like this. And that's where you declare that this at this point, this is the weights that I'm going to use in my prediction, right? So that's roughly how you would kind of implement early stopping. Okay. All right. So this there isn't really much kind of complicated theory around this. It's just a heuristic that you use to kind of prevent overfitting. Uh, the more interesting stuff happens uh, with the techniques of what is known as regularization. So we'll talk about that a bit more. So what is regularization? So the two kind of additional techniques that we're going to talk about are regularization, uh, data augmentation, and the other technique is dropout. Okay, so these techniques are kind of based on the idea of classical statistical learning theory. Uh, in classical learning theory, there is a generalization result or bound, and this comes from a theory called pack learning. PAC stands for probably approximately correct. Uh, I'm not going to cover the theory of pack learning. This is a complicated subject, but the basic idea is that kind of in general, we know that we expect the test error is always usually higher than the training error, because training error is what we actually try to minimize in our learning algorithm. So we can say that our generalization error is the difference between the train error and the test error, right? And this is a positive number because the test error is always greater than the train error. But we can actually bound this, right? And then the way to bound this, the result that comes from the bound that we usually have is kind of, this is usually less than or equal to d by n square root. And what is the value d? D is the a kind of a measure of model complexity. And n is equal to what we call sample complexity. Right? So what are these numbers? So D represents like there are many different ways of representing D. So for example, one measure of D could be how many weight parameters are in your network, right? If you have a really large network with lots of layers and lots of neurons per layer, then you have a large number of these neurons with weights, and that gives you a large network. And that would be a large value of D, right? And another one, like let's say with this example of polynomial fitting, right? So if your degree of your polynomial is really big, that means you have a complex model, right? And n is basically sample complexity is the number of training examples that you have. Okay. So now what this result tells us is that if you really want to have a kind of if you really want to bound the gap between your training error and the test error, which would give you good generalization, you need this right hand side to be very small, right? Now, looking at this expression, can someone tell me how can we ensure that this right hand side is small? Like, what are the ways to make this right hand side small?
In- Increase n.
Increase n. What does increase n mean? So you can make this bound small by you increase n, right? That means that the more data samples that you have or the size of your training data, if you can really train with lots of data, then gives you that would give you better performance, right? So basically the idea is basically what we have in common sense, like to have a good neural network model or a good machine learning model. If you just have like a five data points, it's very hard for you to actually have a good model. But if you have like thousand data points, then you have a much better chance of a good model. So, and this is mathematically proved in this bound where it says that the more data that you have, n is higher, which means this right-hand side is going to be a lower value, and that means you can bound the error in your generalization. Okay, so that's actually related to this technique of data augmentation. What data augmentation means is that we are actually trying to, let's say we have a limited number of, let's say, images for an image classification problem, and then we want to increase the size of our data set. And data augmentation is basically taking our existing data sets or existing images and then making some small perturbations like rotating them or cropping them or moving a few pixels, right? And then using that, you're kind of increasing the number of your data points. And by this theory, that says that that would actually help you have better generalization performance. Okay, so that's one way, and that's related to data augmentation. But from this expression, we also have another way to reduce this right-hand side, right? What is that? What is the other
Reduce
knob we can
model
control?
complexity.
Exactly. So model complexity needs to go up or down.
Down.
It needs to go down. It has a reverse relation as to n, right? So by increasing the number of data points, we can get better performance. Or if we let's say we have overfitting, and then if we can somehow reduce the model complexity, then we can also improve performance, right? So data augmentation means we improve performance by increasing n, and regularization means that we try to reduce d, and dropout is also like trying to reduce d to get better performance. Okay. So for example, let's look at this example here. So if you see here, let's say we have three different fits here, right? Let's say we try to fit with a polynomial like the blue one, and we also try another one which is going to be, let's say, just a straight line. Okay. Now the brown line is a linear equation. So what is the degree of the polynomial of a linear equation? What is the degree of it?
One.
It's one. It's a linear equation, so it's a degree one. And then the blue one here, this is like a quadratic, so it's a degree, let's say, two. And this red one is probably like degree, let's say it's seventh degree polynomial. Okay. So of these three polynomials that we are trying to use to fit our training data, which are like these 5 points here, which one has the highest model complexity?
The degree 7.
The degree seven, right? So basically, we know that our data generating process was a quadratic, but we had some noise. And as we allowed a more complex model like a degree seven model, we actually fit let us fit the data using a higher degree polynomial or more complex model, and we fit to the noise. Whereas the degree two gave us a green curve that looks very similar and kind of has a much better fit to the data. And then degree one was even simpler, and it was actually not a good fit again, but it's for a different reason. So if you can see here, the degree two is actually the almost the right fit, right? It's the right level of complexity of the model, and that's what we try to achieve, right? So the degree seven one, we are going to say that it is overfitting to the noise, right? And the degree two is actually the desired model because it is not overfitting. It's actually the right complexity. And what about the degree one model? What is happening with the degree one? So we said that degree seven is the most complex and degree one is the least complex, right? So what happens if I use degree one as our model? Is that a good model or not?
You would be underfitting in that case, correct?
Exactly. We are underfitting. So when we have overfitting, we have a much more complex model and we try to reduce the complexity with regularization. But we also have to be careful that we don't regularize way too much that we actually don't even fit the data. So this is basically what happens is that we are not using a model that has enough capacity to actually even learn the pattern, right? Because our data is quadratic, whereas we are trying to fit it using a linear model. So the model is not even complex enough. So both are problematic. The underfitting we can actually fix by, like, for example, doing more training or trying a more complex model. In general, the idea is that the way we actually solve these problems is that we allow us to have more complex models, but then we add a regularization to actually kind of bound how much complexity we can have. But if we are always saying that whatever our data is, we're always going to use a linear model, then that will always be underfitting because most phenomena would not be linear, right? So we allow for complex models by having a very large neural network, but then we add regularizers to kind of make sure that we actually have this desired complexity rather than a higher complexity. Okay, so this is the technique of regularization, and we'll see that dropout is another technique which is also related to kind of complexity reduction. And those are the things that we're going to discuss now. Okay, so so the most common way of regularization is called L2 regularization. Okay. Uh, and the idea is that we actually solve this by modifying our loss function, right? So if you have a loss function of our, let's say, weights, right? So let's say we are talking about least squares regression. Then in least squares regression, a we have a training loss term, which is kind of the norm of the difference between our prediction y and our prediction, which is w transpose x for a linear model, let's say, for example, and y is our true label. And then we add a regularizer here. So lambda times a regularization, which is typically a function of your weights, right? And this term controls how complex our model can be, right? And when your regularizer is basically if you use an L2 norm squared, right? Then this is called an L2 regularization, right? And the idea is that if you think back to like this problem here, if you try to fit the curve with a degree 7 model, then what typically happens is that to have these kind of bumps in your curve, you actually have to have very high values of your weight parameters, right? So uh, your what your W is going to be like a kind of a vector like this, right? Uh, so what we are trying to talk about here is kind of polynomial fitting, right? So in a polynomial fitting, uh, our what we are trying to do here is that basically uh, if you have your input x, you are kind of thinking of x as a okay. Let's for this example, let's just say x is just a real number, right? So x square, let's say up to x to the power d. And then your model is W transpose phi of x, right? That's your prediction. And then you kind of like your training loss is going to be like this. This is your train loss. right? And if you so this is basically how you are fitting uh, your data to a high degree polynomial. And if you actually want kind of a wiggly curve like this that kind of runs through all your training data points, right? And you might have a simple data generating process, but you're fitting to the noise. To do that, you would actually have to put very high weight values on these uh, larger uh, degree uh, uh, degree coefficients, right? So it's going to be like this is what it would look like: W0 plus W1 X, right? And this becomes a complex polynomial when these weights are really high. So one way to kind of tackle or kind of lower the complexity is to put a bound on this norm, right? So if you bound this norm or this regularizer term, then you're disallowing these weights to get really big, and that prevents you from kind of fitting a really complex function to a simple data process, to a simpler data pattern, right? So this is the idea of regularization. So your loss function basically becomes basically you have the train loss. uh, you have your train loss which you use in gradient descent. So this is like train. So this is the loss you use in general for, let's say, backprop. And then you have this additional regularizer term. And this is your regularizer. And you usually have like a parameter lambda. Lambda allows you to control how much are you going to penalize a complex model versus how much do you care about the actual training loss, right? So if lambda is really high, then you're going to have more penalty for having a really complex model with large values of these W weights. But if your lambda is very small, then you don't care much about regularizing. You care more about fitting your training data. So with experimentations or hyperparameter tuning, you would actually figure out what is the best value of lambda for your model, right? And now, if this is your model, then what happens to our gradient is that if we take the derivative here, then we have the the train loss, which is the original loss we use, let's say, in backprop. And then you also have this term here, which is going to be lambda times what is the derivative of the square of the norm for W?
Uh, W times one, right? Is that correct?
Exactly. So just W, right? So then now your gradient becomes this. And now if you're doing gradient descent, what will happen is your W gets updated to be eta minus both of these terms here because they're both part of the gradient. So you have your original loss, which is your train loss, and plus lambda times W bar. Okay. And then what this looks like is basically you have W1 times 1 minus some eta lambda minus eta times the train loss. And this is why this algorithm is called weight decay, because at every iteration of gradient descent, What is happening is that you have this gradient term for the training loss. So this is kind of the descending or moving in the direction opposite to the gradient, maximum gradient. And that's the usual gradient descent. But you also have this additional term of where your weight vector is actually being decayed by this factor, right? This value is something that's less than zero, less than one, which means every time you run this, W bar, let's say, gets multiplied by zero point 0.8 or some or zero point 0.7, and you keep doing that, which kind of decays your weights, right? So as you can see that decaying the weight actually is kind of like making the weight smaller and smaller, kind of it gets makes them closer to zero as much as possible, right? So that's how the regularizer works. So this weight decay comes from the regularization term, and this original term comes from just trying to find the derivative of the training loss and then move in the direction of the opposite of the gradient to kind of do the regular gradient descent, right? So that's kind of what happens in this L2 regularization. Okay, questions on this? Okay, so it's a like 9:04. So let's take a like five. Let's take a 10-minute break. Like come back at 9:15, and then we'll continue. All right. Okay, should we restart? Okay, let's get back to the class. So let's talk about the next technique for combating overfitting, and this is called dropout, and it's a very interesting technique. It's related to kind of reducing model complexity, and dropout is typically done for like a multi-layer perceptron or neural network. That's typically where this technique applies because it's about dropping neurons. Okay, that's the main idea. So it's not really so. Like, for example, L2 regularization is something that you can use for like linear models, like a support vector machine or any model. It may not be a neural network, but dropout specifically is for neural networks. Uh, the idea of dropout is kind of we use it to kind of reduce model complexity, but so it's kind of like we said the D parameter, we want to reduce the D parameter, so it's related to that, and it's also related to like some sort of ensembling. So has anyone in a machine learning class looked at techniques like boosting uh, or bagging? Like anyone familiar with these terms, these types of models? No?
I have not heard of those before. I don't know about anyone else.
Okay. So boosting is basically uh, it's kind of a instead of having a really complex model, you have a lot of weak or like simple models, and you just kind of take the prediction of the simple models and kind of somehow do a weighted average of that to get a good model, right? So it's kind of a like instead of one really gigantic model, it's kind of a bunch of small models, and you kind of combine them to get a good result. Right? That's the idea of ensembling, and it's a very popular technique in advanced machine learning. So that aspect of ensembling also kind of can be explained, can be used to explain why dropout works as a good technique. But let's look at the main concept of dropout. So let's say let's consider an example. Okay, so let's say I want to build an image classifier, and I let's say I have 1,000 images, right? Okay, so kind of my number of samples is like 1,000. Okay, so let's say n is 1,000, and I want to train a neural network. Okay, a neural network, and let's say the neural network that I want to design has a number of layers, right? Okay, let's say I have I use like a 20 layer network, and let's say at every layer I have a bunch of neurons, and let's say I decide to put in like uh, 300 neurons per layer. Okay, so what is the total number of model parameters of this network, roughly?
6,000?
Roughly 6,000, right? Like we would kind of uh, try to measure the dimension of the matrices, but roughly you would have kind of on the order of 6,000 parameters. And you can kind of think of this number 6,000 as a proxy for the parameter D, or the model complexity, right? So we have 20 layers, and each layer has 300 neurons. So it's kind of a really kind of a complex neural network, right? Now, if you look at these numbers, right? If I try to train 1,000 image data on a 6,000 parameter model, what do you kind of think would happen here? Would this be a good fit, or we would be overfitting? So here the model complexity is larger than the sample complexity n, right? And we kind of have this theory that the generalization is bounded by d by n square root, right? So in this example, d is, what was it? 6,000, right? And n was like 1,000. That means d by n square root is about like square root of 6, which means that we actually have a big gap between the test error and train error, right? So this number is large, so we expect this to overfit. So we have, basically we can say we have a model that is probably too complex compared to our amount of data that we have, right? So we can expect that this might be overfitting. Okay, so now when we say overfitting, we try to maybe reduce the complexity. And one technique of reducing complexity is, if we see that we have too many model parameters, or in this case neurons, we can say that uh, the idea of dropout is, let's kind of randomly drop a neuron with probability, let's say a value p. Okay. So for example, what do I mean by this? Let's say p is like half, right? The way I'm going to do, what I'm going to do is that during training, at train time, every time I pass through in the forward pass, right? Every time, let's say I have a neuron, right? Let's say this is my neuron, right? It has a number of inputs going into the neuron. Let's say it's a ReLU neuron, and then I have an output, let's say activation A. What I'm going to do is, with probability half, I'm going to, with probability half, I'm going to set this to 0. Basically, let's say multiply by 0, right? Or kind of neglect this activation. In some sense, I'm kind of ignoring the impact of this neuron, and whatever output was coming in, I'm just going to drop it, right? So pictorially, you can think of it like this, right? Let's say I'm just using a simple example of a network. Okay, let's say I have just a few layers here, like this is layer 1 and layer 2, right? And these are my inputs. So my inputs, like two input real numbers, x1 and x2. And it's a simple like two layer, two neuron network, right? So we have connections here into here, Okay, let's call this like neuron N1. This is neuron N2 in the first layer, and these again connect all to a connection. And then let's say this is N3, and this is N4. And let's say they eventually go into an output, go an output like a softmax or something. Right? This is the output. Okay. In dropout, what I'm going to do is that among the four neurons in the middle, I'm going to like randomly sample two neurons and then just kill them, right? So for example, let's say I randomly sample from 1 to 4, and I get to drop N1 and then N4. If that happens, then my network might look like this. So X1 is there. So this neuron doesn't exist. We just directly have N3, and then X2, this goes to N2, and then N4 is not there. I have this, right? And this goes into the output. Okay. So if you look here, instead of four neurons, I actually have just two neurons, and then I have only like three or four way connections. Here I had like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 connections. So I have a simpler model, right? So you can think of dropout as kind of randomly dropping some neurons, which makes the model less complex. And we hope that that would give us a better chance of generalization. That's the basic idea of dropout. Now, let's say I do the training for a batch of input. Every time I have a batch of input, I'm actually going to do this random sampling. Uh, every time I'm going to do a new random sampling. So in my first train step, like step one, this might be my sample network after dropout. But in step two, let's say go through the second batch. In step two, I might not drop the same N1 and N4. Let's say I drop N1 and N2, right? So in step two, let's say I drop N1 and N2, right? In that case, my network would look like X1, X2, right? And 3. Sorry, I meant to say I want to drop N1 and N3. Okay. So if that happens, I just have the two bottom net neurons, N2 and N4. So both of these are going into like N2, and this goes into N4, and that just goes into your output, right? So this also has a similar like lower complexity, like 50% of the neurons are gone. But if you see here, by randomly sampling different neurons to drop, I actually have two different simpler models here, right? So this gives us like an ensemble of different models, which makes the network generalize better. The other idea is that what happens here is that by randomly dropping a neuron, we reduce the over reliance of the network to learn specifically or put too much emphasis on a specific neuron. Because if you're sampling, then there is always a chance that neuron might be dropped and your network is forced to learn without that particular neuron, right? So that makes the network more robust and better at generalizing. Okay. So that's the basic idea of dropout, and it's a very popular technique. And there are some theoretical guarantees as to how it performs, but that's the basic idea. Uh, so this dropout happens during training, and then at test time, you just maybe use the full network, right? Because in when your test time, you don't do this dropout, you just use the full network, but you uh, use the full network without any dropout, but with some scaling to adjust, right? Because when you're doing inference at test time, you're actually using the full network. In this case, you're using 4 neurons, whereas here you're just using 2 neurons on average. So you need to kind of adjust that scale. So that would be proportional to P, right? So there would be a scaling factor here, right? So the in this time your output that you get, you scale by the value 1 minus P, right? Because why is that? Because let's say P is 50% or half, then you scale by 1/2. So your output that you get during test time, you're gonna just scale down by 50%, and that makes the the network that you're getting from the output, the results, on the similar scale as the training time network, because in training time you are dropping 50% of the nodes of the neurons, right? So that's how you kind of adjust the scale at the test time. Okay. So that's the idea of dropout. Any questions? Okay. All right. So that's so the I've kind of talked about uh, we've talked about the uh, practical techniques of dealing with overfitting and improving generalization performance, right? Uh, so now I want to talk about uh, like generalization in like modern deep learning, right? What's the theory of like large scale neural networks and generalization? Now, so this is the kind of the modern view of generalization, and that will be the last topic of today, right? So what's the idea? Uh, so let's kind of think about this. So uh, we we are all familiar with like these modern large language models, right? Uh, does anyone know like for like some of these models like GPT, we're all kind of playing around with this like GPT codex, like and then Anthropic has these models. You have these open source models. Like, what is the kind of the scale of parameters or number of the size of these neural networks of these large language models? Has anyone curiously looked up like the number of parameters of some of these models?
I know GPT, Chat GPT is huge.
Yeah.
It's like 12. I forget the scale. Either it's greater than 12,000. It might even be like 12 million or
I'm
something.
Oh, it's way big. It's going to be on the order of billions, the
Yeah.
latest models. So you basically have a billion parameter model, right? So if you think about it, and these models, we know that we use it for a lot of generalized tasks. Like we use it for, you want to be using it for like code generation. We've been using for like textual tasks, like it kind of we ask it questions, it kind of gives me a good answer, it can solve math problems for me. So they are actually, and they are they might actually like give answers to questions that they haven't seen before. So we kind of, as we are interacting with them, we kind of feel that they are actually not just memorizing the data, but they actually have some capability of generalization. So they are generalizing despite having a huge number of parameters, right? The classical theory that we said is that if I if I want to generalize, like if D is the number of, if I put in like 1 billion in D, right? And then let's say N is like a finite number of input, then we should get horrible performance, right? Because D is extremely large, so this gap would be huge. So we should classically, a large language model like ChatGPT should not be able to generalize, right? So what's happening? So there is a mystery there, right? Because we are talking about here for techniques like dropout or regularization, which is trying to make the model simpler, whereas ChatGPT is like a billion parameter model and it's doing very well. So there is something else going on here, right? So we want to kind of try to understand that a bit. So as an example, let's say I have let's say I have a kind of a some sort of uh, like a let's say this is our kind of a, a kind of a ground truth model that we have, right? And then we have some samples on here, right? Right? Okay. And let's say I I want to fit a one-dimensional line to this, right? So we all know that this might maybe line looks like this, right? So and so what so we have a really simple model. So we expect to be like maybe generalize well, but this actually would be underfitting, right? So so this is an example of underfitting. Now let's say I'm gonna use like d equal to 3, right? So d equal to 3 is actually the same dimension as the data generating process, right? So I might expect this to be like a good fit, right? It might be fitting much well. And this is actually a good fit. And this is like almost right? This is no overfitting or underfitting, right? And that's because we know that the d equal to 3 is the right dimension. Okay. But now let's say I have the same data, right? Okay, and then let's say I have these samples, and then I'm gonna say I'm gonna use d equal to, let's say, 20. Okay, what would happen here for a 20 if I use a 20-dimensional polynomial to fit this data? What do we expect to happen?
Overfitting.
Overfitting, and the function might be like a really complex function with lots of these spikes and turns, right? Because I'm fitting to like a noise, and I'm gonna. So in this example, we have an overfit, right? So we have zero training error because we are passing through all the sample data points, but we can see that our generalization performance is really horrible, right? Because our true process was like a cubic polynomial, but we are just completely overfitting, right? And then classical theory would tell us that if you want a good fit, we should reduce D, right? We should kind of reduce D to like maybe 3 or 4 to get a better fit. Now, but if I think about a modern network like a neural network, have it might actually have very high dimensions, right? So let's see what happens when I do d equal to 1000. So if you try d equal to 1000, right, something really surprising happens. So this is what a 1000 dimensional polynomial fit looks like. Let's say these are our sample points. Okay. If we have a 1000 degree polynomial, surprisingly, what we see is something like this. So we actually don't have a crazy like spiky fit anymore. What we have is like something like this. It actually looks like this. Okay. So this is the fit that we get for a 1000 degree polynomial. So it seems like it's not really overfitting as horribly as for d equal to 20, right? So if you use like d equal to 1000, that's like using like a, you can think of this as akin to using a lot of parameters in your like a chat GPT type model, right? Which has like a billion parameters. So the kind of this is kind of an explanation of why like deep networks like chat GPT are actually doing well, right? Kind of the idea here is that when we have a really extremely large model, then your learned model kind of has two components. It has kind of a simple fit plus some local spikes. So the simple fit is what we use for prediction, right? So you can think of this curve as kind of an addition of two curves. One is that kind of a cubic component that kind of matches the data generating process, and you have these local spikes near the noisy points, right? Uh, and uh, and this leads to the idea of what is called like a double descent phenomena. That we see in these extremely large networks. Okay, so what is our classical view of of generalization overfitting is that we see this, right? We see that your training error goes down with like, let's say d is my model parameter for capacity, and I have like loss here. So this is like the overfitting regime. This is test, and this is train. And let's say here the maximum complexity is like a 20-degree polynomial. You can think of 20 as kind of a classical regime of like smaller scale models. And this is where you would say that I try to maybe train with a smaller capacity to get a better fit, right? Now, with large networks, we have this threshold behavior where we have loss. What we see here is that we can drive our uh, capacity to, we can drive our training loss to almost zero, right? So what happens here is that this is where my model complexity is increasing to, like, let's say 1,000, which is what I'm showing here, where we have this very interesting high dimensional behavior. Okay, this, let's say, like about 1,000. I meant to just 10 cube for space. Okay, so we would expect that classical theory says that at this point we would be overfitting really badly, right? So this is my train. And now what we see is that we kind of have this threshold region where, so for the test, we see that test kind of has this initially this similar behavior where that at some point the test risk, this is your test error, we have overfitting. But when we overfit at, let's say, about d equal to 20, instead of like trying to have a like a simpler model, we actually keep pushing to like a more complex model where we go to d equal to 1,000. And then we see this kind of another descent happening here. And that's the double descent behavior. So this is called a over-parameterized region where we have extremely large number of parameters. And this, you can say, is where most of the modern networks like GPT lie, where we have billions of parameters. This is over-parameterized region where we have extremely large number of parameters. And this is like the classical regime where here we have like under, this is like lower number of parameters, but we know that like this part is like where we are overfitting, right? So classically, we would say if I have overfitting, I'm going to reduce my parameters. But what this surprising phenomena tells us that instead of reducing, uh, right, that's I think that's a very good, probably a link that Bobby is sharing with us. Yeah, thank you. With this extremely large number of parameters, we actually kind of drive down the test loss, which is surprising. So that means that, and that's kind of the reason why we have this like war between all these big companies that have lots of money, that they are just building bigger and bigger models. And that's because of this phenomenon of double descent, because we found out that we can just throw in an extremely large number of neurons or parameters in a model, and I can just drive my test error to very low numbers and have very good performance, right? And this has been shown for like a lot of like models like on datasets like MNIST dataset or some other dataset which we see, where we see that we have this phenomena, right? So this is one a modern view of generalization, and this is where things actually are really open. Like we observe this behavior empirically, that for classical learning, where we are in a like a smaller complexity regime, we have good theory that tells us like what happens. We have these bounds between the complexity of the model and the data size. But in this region, like those bounds no longer work. So we need new theories. And there are a lot of competing theories for this double descent phenomena, or like what happens here. Uh, but that's kind of more state of the art, and we still don't have a good answer in the research community, like what's the right way to think about this. But empirically, we know that if we have bigger and bigger models, we seem to be good. We are not really overfitting. We're actually solving the overfitting problem by just having an extremely overparameterized model. Okay. Now, there are like some ideas around like why this happens, right? Like the one idea is that there are some implicit bias in like things like stochastic gradient descent. Okay. So the idea is that when we allow like millions of parameters, right, then kind of we do stochastic gradient descent on an extremely high dimensional space, and kind of the loss landscape that is chosen by stochastic gradient descent, it has a lot of freedom to choose like which loss landscape to use, and it tends to use a loss landscape that kind of prefers simpler functions, right? So like even though we have, let's say, like million parameters, this may lead to like a simpler function fit, because when you have such a high dimensional space, you have a lot of functions that can give you good a lot of functions can actually fit your training data, and then there might be some implicit bias in your training process like SGD that chooses like simpler functions, and that lets you generalize well. That's one theory here, but there are many other theories, and this is where like things are more advanced and we won't really cover too much here. Okay, so that's all I want to say about generalization. Any questions? Actually, I want to show something interesting. It's kind of this double descent phenomena. Uh, this is a very nice video that shows the double descent phenomena. So let's take a look at this. Okay. All right. So so sorry about that noise, but let me lower the volume and then let's take a look at this demonstration. It's kind of demonstrating the double descent. I'll share this link. So you can see here, basically we have like a kind of a low dimensional polynomial that's kind of, so this is our data is expected to be like a maybe three dimensional polynomial. We are starting with a linear fit, which is underfitting, and then we'll gradually increase the complexity of the fit and see what happens, right? So let's look at this video. It's a 1 minute video. So you see that we are gradually increasing the complexity, right? So, and this is starting to look at as a good fit. We have like maybe one, two, three, four, five, six, seven neurons that are trying to fit this. And you can, down here, you can see the train and test loss. Uh, so if we kind of go back here, this is like starting it, and we just have a simple, this is like a simple perceptron. Okay, now you see here what is happening here. You're increasing to like maybe 20 hidden neurons here, right? You're starting to get like a spiky function, and you can see here the red line is the red line is your training loss, which is almost zero because we are able to approximate this function using universal approximation theory. We can approximate this to almost zero training error, but you can see the test error is going up, right? That's the classical overfitting regime, right? Okay, let's continue looking at what happens. Okay, now you can see that now you've kind of raised the number of neurons to be like really, really big. Maybe it is like 100 or 200 neurons. And you can start to see that maybe there is another descent happening in the test loss, right? So let's continue seeing that. Okay, so now you can see that it's like we're trying to get this hidden neuron count to almost like really large, right? Uh, and then you can see that the blue line initially it was going down, it then increased, and it increased about like what is it like 10, like around maybe around 30 neurons, right? This is like 30. That's where we have this again overfitting regime. But then if you go beyond like 100, we are starting to, or 1000, we are starting to get like again a decrease in the test loss, right? So if you keep going here, so this is showing that they are rerunning this experiment with different like different runs, and you can see that on average, you the test loss. So the train loss is always going to zero because we are over parameterizing by using like 1000 neurons here. And then the test loss is there is an initial spike in the test loss, and then you have another descent which kind of drives it down to zero, right? So let's continue seeing what happens here. Right. So this underparameter regime is the classic picture of overfitting, right? So this part is underfitting, and then this part is your overfitting regime, where your training loss goes to zero, but your test loss is increasing, right? And this is where you would use techniques like dropout or L2 regularization to kind of reduce the model complexity. But then this yellow region is where you have over-parameterization, right? And this is where by instead of like lowering the complexity, you're going in the opposite direction where you're increasing the complexity to like thousands of neurons, right? And that's where your kind of test loss again starts to go down here, right? So this means usually like small neural networks, and modern means like ChatGPT, uh, like Grok, Codex, these types of like extremely large billion parameter models. That's where we observe this behavior, right? So you can see this is like classical underfitting where both your test loss and train loss is high, which means that your model is too simple. And then you have this classical optimum, which is kind of where you want to be for like optimal performance for a small scale model. And then you have this overfitting regime where your training loss is zero, but your test loss is very high, right? That's your overfitting regime. And finally, you have the modern over-parameterization regime for like models like ChatGPT, where your test loss is also going down to a very small value along with the train loss. So train loss is zero means that you have a lot of parameters and you are be able to kind of fit or kind of get the train loss to zero, but your test loss also is very small, which means that you have extremely good generalization performance. Okay. So hopefully that was interesting, and I will kind of share a link to this in the Canvas page. All right. So that's it for today. Any questions? Okay.
Professor, I had one
Yeah.
about the overfitting
Yeah.
because does it eventually when you're extremely over parameterized, does it eventually the error start increasing again? Because I would imagine if you truly had a function that tried to replicate or had
Mhm.
to replicate every single one of those values, you would have to have some kind of a you'd have to go back to some kind of a spiky graph to do that.
Yeah. So there is not we don't have a theory for deep learning that kind of explains that, but empirically, what has been seen by like large foundation models that are extremely large like ChatGPT is that that doesn't happen. Like we have empirical evidence that as you keep getting bigger and bigger models, like going towards infinity in terms of model size, the test time performance gets like just keeps getting better. Which is and we have something like we have these thresholds where we once we kind of just instead of doing anything else, if we just kind of invest in larger and larger models by just increasing the compute and kind of letting train using just backprop and stochastic gradient descent or momentum, what we see is that we keep getting these regimes where we kind of unlock new behavior, right? We kind of have more capabilities in the models, even without kind of any smart techniques. And that's kind of like due to this. like double listen where kind of the test loss keeps going down smaller and smaller, and we kind of get better and better performance. So it might intuitively seem that maybe there should be another spike, but empirically we haven't no one has seen that spike yet. Like it just keeps staying low. Uh, Again, that might be something to kind of do some more research, or I read some more papers on that. I'll try to share some links to articles related to that. But empirically, we see that it doesn't happen, but maybe there is some theoretical justification for that. Uh, you might think that maybe there should be another spike, but we haven't seen that spike.
Gotcha. I also had one other question. Back to
Yeah,
the part about the it was the ratio between the target versus train, or train versus test, where it was complexity
this one,
over complexity of the, yeah, that
this one,
one.
right? That yeah.
Um, does the sample complexity also include things such as maybe uh like the amount of parameters in like the size of the input? Like say if it's like a picture, like the
No,
resolution of the
yeah,
picture, just for instance.
that's a good point. But when you're talking about like this, usually means like you can. I mean, there are when you have a decent number of samples, kind of the number of data points kind of dictates this complexity, uh, and then that might just be a constant multiplier, kind of like you might have just like cn instead of n, where kind of c is kind of uh, like the number of pixels per image. So it's kind of compared to n, it might be much smaller. But overall, the sample complexity usually denotes kind of the number of training examples that you have in your problem.
I see.
Yep.
Thank
Good
you.
questions. All right. It's 10 p.m. So if there are no more questions, we can end today, and I will post the video and a few links uh, in the Canvas page. One question, like I see in the chat that like someone is saying that they cannot still access the Canvas link to the MNIST dataset, but I shared in the announcement another link to the dataset. Has anyone tried to? Maybe can someone try to click and see if you can access that from the Canvas announcements? I'd like to verify that like folks are able to kind of get the dataset for their assignment. Yeah, let me know. Like maybe check in a few seconds, maybe, and let me know. If at least one person can do it among the three of you, then I would say that means probably everyone else can be able to do it. So it's if you look here in the announcements, it's this one. Right? Can folks see if they can access this?
Yep, I can access it.
Okay. So can you then reply in the Discord channel that and just share this link in the Discord channel so that everyone else can also
Yep,
uh,
I can
use it.
I can do
All right.
that.
So you can use this for your as your data set. This is the same thing, just a link that works. Yeah. All right. Thank you. Okay. I'll see you guys next week. All right.